Okay, great. So, what is organic chemistry? Organic chemistry is the study of compounds that contain the element carbon. So, as you can probably guess, there are a lot of organic molecules and they're found all around us. Some common organic compounds include clothing, food, medicine, gasoline, and soaps. So if you have ever cooked with a gas stove, the gas that is used is methane, and this is an organic molecule, and ethanol, which is found in alcoholic beverages, or again, when we were all using a ton of hand sanitizer, ethanol is also an organic compound. So there's some common characteristics to organic molecules. All organic compounds contain carbon atoms, and most of them contain hydrogen atoms. So we are going to look at a bunch of organic molecules during this lecture, and you will note that they all have carbon and they all have hydrogen atoms. As we learned in our covalent bonding lectures, and also, when we looked at periodic trends, carbon likes to form four covalent bonds and hydrogen forms one covalent bond. So you'll often see a carbon hydrogen single bond in organic molecules. And while these compounds contain carbon and hydrogen, they can also be bound to what is called a heteroatom. And this is an element that is not carbon or hydrogen. So, for example, oxygen, chlorine, and nitrogen can all be found in organic molecules as well. We call them heteroatoms because they're different than carbon and hydrogen. So here we're showing an example of methane again. This contains carbon with single bonds to hydrogen, and you'll note that the carbon has one, two, three, four bonds to it. And then here we have acetic acid, and we'll understand why this portion is highlighted in red in a few slides. But you'll see that while this organic compound does contain carbon and hydrogen, it also contains the heteroatoms of oxygen. So, carbon in organic molecules can form single, double, and triple bonds, but it cannot have more than four bonds to it. So, and if you have a molecule where you have a carbon atom that's surrounded by four atoms, it's going to form single bonds. So, this here again in our example of methane, you can see that the carbon is surrounded by four hydrogen. If the carbon is surrounded by three atoms, it forms one double bond. So when we think about this, we have to first isolate one carbon. So in this organic molecule, there's two carbons. Let's pretend that we're covering this carbon on the right up. If we focus just on the carbon on the left, we see that it has a hydrogen bound, another hydrogen bound, and then it has a double bond to this other C. And so that is three atoms in essence, this two hydrogen and this one carbon. And that's why it's forming this double bond here because the carbon has to form four bonds. And then if you have a carbon atom surrounded by two atoms, then it generally forms one triple bond. And again, that's because each carbon needs to have four bonds. So this atom here has carbon, it has a single bond to hydrogen, and then it has a triple bond to carbon. And that leads us to have four bonds in this molecule. So you will see all of these types of bonds in organic molecules, and they all have different names, which we'll learn about in a few slides. These carbon compounds can be straight in structure or cyclical. So this molecule that we're showing on the left is a straight structure. It's linear. And then we have a molecule called cyclohexane, and you can see here that this molecule is actually in a circle or cyclic, a ring type structure. So now we're going to learn how to draw organic structures. Um, we learned in chapter 4 how to draw Lewis structures, but sometimes organic molecules can contain many atoms and they can be very long. This is to prepare us for when we start to look at biomolecules such as fatty acids. They can have 16 carbons, 18 carbons, 22 carbons, which are very long. And you could imagine that it would take a really long time to draw a Lewis structure with 16 carbons in it. So what we like to do is draw condensed organic structures. And the way to draw this is that you take out the straight lines that indicate the bonds, and then you use these symbols to indicate the atoms. So if you have a carbon bound to one hydrogen atom, that's represented as a C and an H. If you have a carbon bound to two hydrogen atoms, you have a C, H, and a subscript of 2. And if you have a carbon bound to three hydrogen atoms, you have a C, H, and 3. So these are common symbols that you should be familiar with. And here's an example of us taking some Lewis structures. And again, you remove the bonds that indicate the lines that indicate the bonds. And then so this example, this carbon has 1, 2, 3 hydrogen around it. So it becomes CH3. This carbon has 2 hydrogen around it. So it forms CH2. The same thing here is CH2, and then O and H to indicate this OH here. Another way that we can draw organic molecules is by drawing a skeletal structure. And skeletal structures are used for organic compounds that contain both rings and chains. We're going to assume that there is a carbon atom at the junction of any two lines or at the end of any line. And we're going to assume that there are enough hydrogens around each carbon to give it 4 bonds. And then you draw in all the heteroatoms and the hydrogens that are directly bonded to them. So we're looking at that molecule again, cyclohexane, and this is the Lewis structure of cyclohexane. To draw a skeletal structure, we're going to take out the symbols for the atoms. So this is kind of the opposite of the condensed structure, where in the condensed structure, we took out the lines and we left in the symbols. And in this example, we take out the symbols and we leave in the lines, except for the hydrogen. So to draw a skeletal structure, you would just draw the lines of your cyclic ring. And the assumption is that anywhere that this 2 lines meet, there's a carbon here. And then we're not going to draw in the hydrogens. We're just going to assume that the hydrogens are there. And this is really helpful when we draw really complex molecules. We will talk about steroid molecules, which are cyclical molecules, and they can have a complex structure, and drawing a skeletal structure helps. Now we're going to discuss the shapes of organic molecules, and this is similar to what we learned about with other molecular geometries of covalent compounds. Molecules form shapes that allow the lone pair electrons and bonds to have the most space separating them. So we already learned about this before, and we'll be talking more specifically about carbon. Remember that carbon likes to form 4 bonds. So a carbon with 2 bonds forms a linear structure, which is a 180-degree bond angle. A carbon with 3 bonds forms a trigonal planar with a 120-degree bond angle, and a carbon with 4 bonds forms our tetrahedron structure with a 109.5-degree bond angle. And these should look familiar, where we're talking about the electron groups and how that dictates what that structure will look like. So we've seen before this linear structure with a 180-degree bond angle, this trigonal planar, which has 120 degrees, and then a tetrahedral, which has 109 degrees between these bond angles. So let's do just a little check-in. You can answer these questions by giving your answer in the chat. Which of the following is considered an organic molecule? You can put either A or B in the chat. Great. So I'm seeing the answer B, and that is correct. This is ammonia, which does not have a carbon in it, so it is not an organic molecule. And this is an organic molecule, and this is an example of an organic molecule that has a heteroatom or chlorine in it. And our next question, you can answer true or false. Organic molecules only contain carbon and hydrogen. Great. And I'm seeing a lot of false, and that is correct. You can have other atoms, such as our previous example, where you have chlorine. Wonderful. So now we're going to discuss functional groups. A functional group is a specific group of atoms attached to a carbon skeleton that has certain physical and chemical properties. This is extremely important as we take this information of organic molecules and extend it to DNA, fatty acids, proteins, the biomolecules that make up our bodies. We'll see that depending on the functional groups, those biomolecules are going to behave differently. We'll be discussing three functional groups today. The first are compounds containing a carbon-hydrogen bond and only carbon and hydrogen. These are called hydrocarbons. The second are compounds that contain a carbon heteroatom single bond. And the last are compounds containing a carbon with a double bond to an oxygen. Our first functional groups are hydrocarbons, and they are organic molecules that only contain carbon and hydrogen. Within this main functional group of hydrocarbons, there are some subgroups as well, and that depends on how many bonds that carbon is making to another carbon. And there are some visual representations in the next slide, but here are the names for the subgroups. So alkanes have only carbon-carbon single bonds. Alkenes have carbon-carbon double bonds. Alkynes have carbon-carbon triple bonds, and aromatic compounds contain a benzene ring, and a benzene ring is a 6-carbon ring with 3 double bonds. Some of the characteristics of hydrocarbons, specifically alkanes, are that these carbon-hydrogen bonds are non-polar, and they often undergo combustion reactions. So for example, methane, propane, and butane are all hydrocarbons, and these are things that we burn on our stoves and our grills in order to create fire. So here is a list of the hydrocarbons functional groups and examples of each. Here you can see an alkane just has a R and H. So when you have an R group, this is just signifying that there's a carbon here bound to a hydrogen. This is the condensed structure. And this is a 3D representation of what this molecule can look like. The carbon atoms are shown in black, and these hydrogen atoms are in white. So you see that there's this carbon single bond, and then there are these single bonds to hydrogen. Here we have this alkene group. This has a carbon, and a double bond here. And you'll see here that in this 3D representation, I'm sorry, this isn't super clear, but you have the carbon, the double bond is in between. And because we have that extra bond in between, we only have 2 bonds, 2 hydrogens on either side. So that's compared to the 3 hydrogens that are in the alkane group. The alkyne group, again, is just adding a triple bond here. And you can see now that instead of 2 hydrogens bound to the carbon, because we have 3 bonds here, that we have just 1 carbon on each side. And then this is what an aromatic compound looks like. So we have this 6 carbon ring, 1, 2, 3, 4, 5, 6. Remember our skeletal structure. And here we have 1, 2, 3 double bonds. And this is what we call a ball and stick model of what this would look like, where the carbons again are in black. And because we drew this as a skeletal structure, we have that the carbons have one hydrogen bound to them. The next functional group that we're going to discuss are when we have a carbon heteroatom single bond. So remember, heteroatoms are any atoms that are not carbon or hydrogen. And there are 4 groups within this category that we're going to focus on. Alkyl halides, and these are compounds that contain a halogen, which are fluorine, chlorine, bromine, or iodine. These are group 7 elements on the periodic table. We have another group that has alcohols, and this contains a carbon bound to a hydroxyl group or an OH group. So we saw this molecule, an example would be ethanol. We have ethers, which are 2 alcohol groups bonded to, 2 alkyl groups bonded to an oxygen atom. So sometimes you'll see alkyl group, and what that means is that you have this carbon CH3 or CH2. And then we have an amine, where 1 hydrogen of ammonia is replaced by this alkyl group or a CH3 group. So let's take a look at some examples. This is what your alkyl halide would look like. So we have this CH3 molecule here, and here we'll have the bromine with its lone pair electrons, and bromine is part of this halide group or group 7 on the periodic table. This is what that 3D structure looks like. So you have the carbon with its 3 hydrogens, and then this molecule is represented in red because it is different than the other molecules. It's not carbon and it's not hydrogen. Then we have our alcohol groups. So again, we have our CH3, and what we're really going to look for is this oxygen and this hydrogen that have this single bond here, and it's represented in this 3D structure where the carbon has its 3 hydrogens. This molecule is representing the oxygen, and this molecule is representing the hydrogen. Then we have an ether group. And one way to remember this is that you're going to have an R, oxygen sandwiched in between 2 other groups. Now, the reason why we represent this as R is that you can have molecules that can be really, really big. And so this R could be 16 carbons. This R could be 20 carbons. And we don't want to have to draw that all out. So what you're going to look for is an oxygen that is sandwiched between 2 groups. Here is a representation where this oxygen is sandwiched between 2 alkyl groups, and this is that visual representation. We see that our heteroatom is in the middle with our 2 alkyl groups on the left and the right, and then our amine group, and you have dealt with compounds like this because this is where we get some of our nomenclature for amino acids. They will have this NH2. That's what you're going to look for. So RNH2, or you can have RNH3, and we'll see what that looks like when we get to our amino acid lecture and protein lecture later on in the class. This is an amine group that is bound to an alkyl group. So what you want to look for is this nitrogen with hydrogen, 2 hydrogens bound. And in this model, the nitrogen is indicated with a blue ball here, and you have these 2 hydrogen atoms, and it's connected to that alkyl group. So these are all of the carbon bound to a heteroatom functional group. Our last functional group that we'll talk about today are C double bond to an O, And this is characterized, this is called a carbonyl carbon. And I am showing what this looks like. Again, our R group is the rest of the molecule, but what should stand out is that you have this carbon with a double bond to an O. And I'll have these two sets of lone pairs. And this carbon that's bound to the oxygen is called a carbonyl or a carbonyl carbon. We'll have three subcategories, and there are some other ways to divide these even further. For the purpose of our class, we'll just focus on these three subgroups. You can have an aldehyde that has a hydrogen atom that's bound directly to the carbonyl carbon. So instead of this R group, you would just have a hydrogen. We have carboxylic acids, and we will see this again when we look at amino acids, because amino acids have an amine group and a carboxylic acid group. So carboxylic acid has an OH group bound to the carbonyl carbon. So instead of an R here, you'll have an alcohol group that we saw in the last slide. And then for an ester, it contains an OR group bounded to the carbonyl carbon. I apologize. And then we also have an amide group. So there's four categories here that has a nitrogen and a hydrogen R group that are bound to the carbonyl carbon. So what we want to focus on is this carbonyl carbon, and each sub-functional group just changes in what this R group is. So let's take a look. For our aldehyde, you'll see here that you have this carbonyl carbon with its double bond to the oxygen, this alkyl group, the CH3 on the left, and just one hydrogen. So this is what you want to look for. A question that you could get on exam is that you have a big molecule, and you'll see this in the practice that you'll do today. It'll say name all the functional groups in this molecule, and it could be a relatively large molecule, and a molecule can have more than one functional group. And what you want to point out and see is if there's this carbonyl carbon double bond O and then this hydrogen. We don't need to talk about ketones today, but this just has two alkyl groups. Instead of a hydrogen, it just has an alkyl group that's on the right. Then we have carboxylic acids, so carbonyl carbon, and then this alcohol group. So this whole group here is called a carboxyl group. And this is where we get our carboxylic acid, this hydroxyl group on the right. We have this ester group. So you have here another oxygen. So this carbon is sandwiched between two oxygens, and then an alkyl group, or this can be different. For this example, it's CH3, but it could be a completely long chain of molecules. But you just want to be able to identify. I always like to think of it of this carbon that's sandwiched between two oxygens. And then the last is our amide group. So this carbonyl carbon is attached to an oxygen and also a nitrogen here. So the carbon is sandwiched between an oxygen and a nitrogen. So let's do another little bit of practice. You can give your answer in the chat. Which molecule would be part of the carboxylic acid functional group, A or B? Great. And I'm seeing the answer A, which is correct. This has our double bond O and our OH, which is our hydroxyl group, this alcohol group. And note that this is a skeletal or kind of skeletal structure because the carbon is here, but we are noting those hetero atoms in the hydrogen that are bound to them. And this is actually a ketone because it has those two methyl groups or alkyl groups on this side. Okay, which molecule would be part of the alkane functional group? A or B? So the correct answer would be A, because this is a benzene ring with those three double bonds and the six carbons. This is an alkane functional group because it only has carbon hydrogen single bonds. This was kind of a trick question. They are all hydrocarbons, but this one has the carbon hydrogen in a linear fashion, and this is that aromatic group. Okay, so lastly, we're going to talk about some properties of organic molecules. Organic molecules exist as individual compounds with much weaker intermolecular forces that exist than what exists in between molecules. So we're going to talk about intramolecular forces and intermolecular forces. Intramolecular forces are forces that hold atoms together within a molecule. So an example of this would be our ionic compounds, where you have one atom that has a positive charge, another atom that has a negative charge, and those are attracted to each other to form that bond. That is a very strong bond. Intermolecular forces exist between two molecules. So that would be if you had one molecule of salt and another molecule of salt, or better example would be one molecule of water and another molecule of water. Those two molecules also have forces in between the two of them. And those are what we call intermolecular forces. One characteristic which we talked about before is polarity, and that is a characteristic that can influence some intermolecular forces in between molecules. Covalent bonds are nonpolar when two atoms have identical or similar electronegativity, and covalent bonds are polar when atoms have different electronegativity. And for this example, because we are focused on carbon for our organic molecules, this often happens when we have carbon bound to oxygen, nitrogen, or any of the halogens that are in that group 7 of the periodic table. So properties of organic molecules, these intermolecular forces that exist. The first one we're going to learn about are London dispersion forces, and these are weak interactions that happen due to momentary changes in electron density in a molecule. So when we talked about atomic structure, we talked about how you can have electron clouds, and that the electrons are always moving around. They stay around the nucleus, but they are moving. And sometimes when this happens, you have an uneven distribution of electrons. So in this example, we're looking at helium, and it has two electrons. Sometimes the electrons can all be on, for this example, the left side of the molecule. And because of that, you have this instantaneous moment of one half of the atom or molecule being negative and one half being positive. Because if you have most of the electrons on the left, then you don't have them on the right. And that means you have this momentary negative charge and momentary positive charge. And when this happens, let's say you have a solution, you can have these instantaneous dipole moments when we have a minus and positive, and multiple atoms in that solution. And because of that, positives and negatives attract. So you can have some forces that occur. So this positive charge that's on this atom is attracted to this negative charge that's on the other atom. And these are very, very, very weak because in an instant, now you can have the negative charge on the other side, or they'll be evenly distributed. We see this type of intermolecular force a lot in nonpolar molecules, particularly very long hydrocarbons, and we'll see this in detail with fatty acids that are very long chains of carbon and hydrogen. So while these forces do exist, they are extremely weak, and they are found in hydrocarbons or nonpolar molecules. Another type of interaction that can happen are when we have dipole-dipole interactions. These are attractive forces between the permanent dipoles of two polar molecules. So a dipole is when you have this slightly positive charge and then a slightly negative charge. Unlike our previous example where it was instantaneous or momentary, where the electrons are moving around, these are um, permanent. So these are when you have um, polar molecules because you have those differences in electronegativity. And the slightly positive part can react with the slightly negative part of a molecule, and a slightly negative part can react to a slightly positive on the other end. So you can have attraction in this formation, you can have an attraction in this for B formation here on the right. And because these are more permanent, dipole-dipole interactions are stronger than your London dispersion forces. The last one that we're going to talk about is hydrogen bonding, and this occurs when a hydrogen atom is bound to oxygen, nitrogen, or fluorine, and it is electrostatically attracted to an oxygen, nitrogen, or fluorine of another molecule. Hydrogen bonding is um, found in water, and this is what gives water some of its unique properties that other solvents don't have. So if we look at this molecule of water, we see oxygen, and we've seen this example before because oxygen is more electronegative than hydrogen. We have all of the electron density on the oxygen and not on the hydrogen. So these are going to be positive and positive, and this is going to be negative. And you could see a situation where if you have a glass of water, there's another molecule of oxygen, of water, that also looks very similar. So it has its oxygen here that's negative and these hydrogens that are positive. And what happens is that the slightly positive hydrogen bonds to or forms an attraction, not a bond, sorry, is attracted to the slightly negative on an oxygen. And again, this could happen if you have nitrogen in this position and fluorine in this position. So this is hydrogen bonding. So lastly, we're going to talk about solubility, which we discussed in our solvents lecture. And I hope that you can see how all of our general chemistry principles are being applied to these organic molecules: polarity, molecular geometry, electron density. All of this is very important. So when we discuss solubility, there is one rule that like dissolves like, and this is true for organic compounds. Most organic compounds can be dissolved in organic solvents. And on the next slide, I have a list of some common organic solvents, but this is a rule that you want to use an organic solvent to dissolve an organic compound. Hydrocarbons and other nonpolar compounds cannot be dissolved in water because they are nonpolar or hydrophobic. And then polar compounds are water soluble only if they are small and contain a nitrogen or hydrogen atom that can hydrogen bond with water. So one of the things that you want to look at is that what you have to do is you have to break these hydrogen bonding forces between the water molecules in order for another compound to be dissolved. And that is very difficult to do. And we talked a bit about this in our solutions lecture as to what happens when you actually have a compound dissolve in water. So on this slide are some common organic solvents. And what you can see is that these organic solvents look similar to some of the functional groups that we discuss. So benzene is an organic solvent. You have acetone here that has that carbonyl carbon here. You have toluene, which contains a benzene ring and a methyl group or an alkyl group. So this is why like dissolves like. This is why organic solvents are great, because these organic solvents look like some of the functional groups or some of the molecules that we might want to dissolve them in. So our last question before we end our lecture today would be, would this molecule be dissolved in water or soluble in water? Yes or no? So the answer is no. And the reason why is because in order for a molecule to be dissolvable in water, it has to be small. So this is actually a fatty acid, which will segue into our next lecture that we're going to have next week. It has one, two, three, four, five, six, seven, eight, nine carbons. And so it is relatively large. So although it does have this carboxylic acid group on the left side, it is simply too large to dissolve in water. And you have this massively large hydrocarbon, which is nonpolar and would not dissolve. So, again, that was a little trick question, but these are some things that you want to look at and just pay attention to. Anytime you see something really large, then small would be probably a molecule that just had one or two carbons attached to it. Anything with nine carbons is going to be relatively large. So maybe if you just had this and a CH2 and a CH3, then it could dissolve, but you do want things to be small. But very good question. And in our next lecture, we'll talk about fatty acids, and because they're long and they're nonpolar, that gives us some of the characteristics that we have of fats and lipids.